Hey everybody, so today I hope to showcase two things to you overall. The first thing that I want to showcase is swarm algorithms, which is what we're going to use for the basis for all of this. And the second thing that I want to show you, and the big thing overall that we're going to go through throughout this, is to show you that probability isn't necessarily probability, that there's multiple ways to measure probability, and that this comes into um, when you can say that like statistics is lies, and you know that there's different ways that you can measure statistics. This goes into a large part of it, right? And then so I figured I'd take a topic that I think people would be interested in, and then this is called Blackjack swarm. And then so uh, I'm utilizing, so again, swarm algorithms, and then creating different simulations of Blackjack based off of, and probability based off of different algorithm types. So Monte Carlo in this instance. It's important to highlight overall, and I do want to highlight that even though I'm using Monte Carlo as like the optimization method for the swarm algorithms, the swarm is always going to utilize um, Gaussian probability. And then so it's like we're going to be sampling from Gaussian probability, which is like the imaginary probability space, because we have to create a probability space for the swarm to operate within. But then uh, from there, the optimization method in this instance, in this first instance that we're looking at, is for Monte Carlo. And then so what we're looking at is the algorithm runs, and then we have our simulations of, it runs through 1,000 hands, and then it runs through in 2 seconds. I'll run it again. Already done. Now it's plotting. Takes a few more seconds to plot. Cool. There we go. And then so now we have our plot and our graph. And then so what we're looking at and what it's demonstrating here is essentially the results of the simulations of 1,000 hands. And so this is what the player's hand is, and then this is what the dealer is showing. So if the player is showing 12 to 21, and then the player has a 12 to 21, and then the dealer is showing 1 through 10. And then just a few statistical things that I want to highlight here, and I've shown, and I've noticed throughout this, is that so like having 12 and then the dealer showing 6, you're actually like in a strong position to stand. And then there's actually like in a lot of instances where 12 kind of like is like a good place to, like, you have more probability to like to stand, and like probability actually increases in weird ways once you go towards 12. Like for example, if the dealer is showing 10 and then you have 12, like it's kind of like good. Or if you have 9, if the dealer is showing 9 and you have 12, like it's really good in those instances to like maybe possibly stand. And it's like it becomes anomalous to stand in those instances. And then what you can see is that like your odds like over to win over 50% only get like over 50% in any instance when you get when you have 18. And then it's of course like your best odds are when the dealer is showing 6 overall. But so overall, if we run this multiple times, we get different simulations, right? Because it's simulating 1,000 hands over every single time. So we'll get like slightly different odds of this. But what like I want to showcase is, first of all, this is the Monte Carlo method of this, right? And then the next method that we can look at is Bayesian probability. And then so Monte Carlo probability is it's created by a casino, by the Monte Carlo casino, right? And then it's essentially simulated. It's simulated probability, which I like because it's like really similar to Gaussian probability in that sense. But like Gaussian probability takes it a step further, where it's creating like kind of like a box and a area for the simulation, whereas Monte Carlo is just, you can simulate anything, and you just throw everything in the Monte Carlo algorithm to simulate, right? And then so it simulates outcomes, and then that's what's happening there. And then with Bayesian probability, what we're looking at is essentially like Bayesian probability like ignores kind of like what's going on with the neighbors, which it makes it kind of like odd for swarm algorithms overall to run, because it's like each one of these guys is running more independent in this instance. And then Bayesian probability has a kind of a problem that we'll highlight here with when it comes to swarm algorithms and particularly interacting with Gaussian probability, where it really wants to look at like the high end of everything, right? And then so when we look at Bayesian optimization as opposed to our Monte Carlo optimization, we can see something very straightforward here, right? Which is that it's showing only like that it's showing like every hand is a losing hand, and it's only showing essentially where there's only like good odds from 17 forward, right? It's saying that and everything like you should hit if the like if you have 16 and the dealer is showing 1, you should hit. Is essentially what it's showing in every single instance, right? No matter what the circumstances are. And then it's like skewing the odds down a lot. And then we can see that we kind of have this, like we see this kind of reverse effect on the 6 that we would expect from other like actual like simulations and actual odds cards, where we would see higher odds here, right? Because like the dealer has to hit here, and then so like and the dealer has a high probability of busting, and then as long as like so, just interesting overall to see those odds and how that's playing out there overall, and especially that it's playing out. Oh well, I guess that makes sense that if the and again that it's playing out that if you have 21 and then the dealer is showing a 6, that you have very low probability of winning that. Like that's not accurate. And then same thing here with 2, right? Like not accurate. Like and then so this is just essentially like the like Bayesian probability I expected going into this and highlighting this overall, that like it would come out something like this, right? Because it's this is as far as a probability method and as far as what swarm algorithms do, this is like as far like not this is as far as like as far removed from each other as I can get. Like these are like incompatible with each other, and then so we get kind of like incompatible data from it, right? And then so the next one is just pure Gaussian probability, which is like essentially like what these are based off of. So this is particle swarm optimization (PSO), and then like standard swarm optimization, and then standard like probability strategy and probability modeling. And then so again, it's just creating it's almost the same. It's really similar to Monte Carlo, with the addition that you're creating like the boundaries and creating the box, right? And then that's the same with the optimization methods. And then so we can see here, this looks a lot more similar to the Monte Carlo distribution, and then we can see that we have kind of the weird anomalies that we saw with the Monte Carlo as well, where we get in this 12 and 13 range, and then if the dealer is showing 6, it's like really good strategy to hold on in a lot of instances. On like if you got 12 or 13 and dealer showing 6, like in a lot of these simulations that I've run, and almost every single one, like it's like I would hold in that instance. And then also too, if you've got 12 or 13 and then dealer showing 10, then like it's like see the odds go up weird, right? Like because it's if you got 14 you should hit, if you've got 15 you should hit, 16, 17 you should hit like up until like 18, right? But then up here, like the odds get a lot higher. Like so, just stand on 13, stand on 12. If the dealer's showing 10, and like you're gonna win like a lot more odds on that than you would think. Like it's kind of like what these simulations are pointing out here. But so overall, to me, this looks very similar to the Monte Carlo, which is very expected, right? Because it's we're playing with the same probability methods, but we can see that there is differentiation and deviation within this, and especially within the odds when you get close to like if the dealer has or you have 21, then like this is skewing the odds lower than the Monte Carlo algorithm was, saying that you're going to lose a lot more if you have 21 in these instances, or push a lot more. And then the last one that I want to show off within this is it's one that I created. It's called Blackjack swarm. And then so Blackjack swarm is particle swarm optimization. Plus, it utilizes evolutionary algorithms and mutation genetic algorithms. And then so the addition to this is that the algorithms kind of like they get more adjustments in between over time. And then so what we can see here is that like as a result of that, like these adjustments that are happening in between, we get like to me it's a much more accurate overall simulation as to the odds, right? Um, in general, our odds are really low across the board unless we have 18, 19, or 20, or 21. And then that's when our odds start to get really good. Although, again, like no matter in every single one of these except for the Bayesian one, which doesn't show any data here, we have really odd odds here at 12 and 13 when the dealer has 10. And like this is across multiple thousands, like at this point, 20,000 simulations probably with all of the data that I've run, you know, and all of the testing and all of this. And then again, like really, like if the dealer has 6, like almost no matter what, like if the dealer has 6 and you have 12, really good odds to hold. Like just stand there on 12, dealer's gonna bust out. And then like except for your lowest odds in this, like in this whole entire chain, come at 15. If you've got 15 and dealer has 16, you might want to hit. And then that's when that's your lowest odds at that point. But like even then, you're good to stand on like 15. If you have 15, dealer has 16, you're really good to stand. And then if you have 15, dealer has if a dealer is showing a 7, your best option is to stand because you're probably going to bust out more often than not. I think is what it's kind of showing, and like I assume that's what the data is carving out within that. But so overall, showing a few things within this. One is the power of swarm algorithms within this, and then how like this reason why this is powerful with these swarm algorithms is because of what parallel processing within this, right? So I'm running agents within this. So these agents are like let's say 1,000 agents per each one of these, and then simulating 1,000 hands, right? And then so each individual agent is like its own individual CPU, gets like its own individual CPU, like its own individual calculator, essentially. And then so I've got like essentially like 1,000 calculators that I put together, and then they run individually and all at the same time. And then I get at the end to like put all of that data together and then put it through here, and that's what allows it to compute so fast. So like I can do 10,000 games with with my 30 swarms in this instance, and then simulate all throughout, right? So kind of just interesting how it plays out overall. But so I'll leave a link to this collab notebook overall, and then this is just again showcasing more around probability and swarm algorithms. So if you like this type of content, please like and subscribe. Thank you very much.